Welcome to lesson 2.3, using deductive reasoning to verify conjectures. The learning target or objective for this lesson is to be able to define and identify deductive reasoning, that's the first one, and two, to be able to use the laws of detachment and law of syllogism. So, the first thing we're looking at is remembering what inductive reasoning is. So we're going to look at several examples of inductive, or at least a couple examples of inductive versus deductive reasoning. The first one, inductive reasoning, is based on an observation and looking at patterns to make a conjecture. So if we're figuring out the pattern, if we are drawing conclusions based on patterns that we are observing, that is inductive reasoning that we're using. Deductive reasoning is based on facts, definitions, postulates, and proven theorems. So we make a conjecture or draw a conclusion based on facts, postulates, and proven theorems. So when our conclusion is based on something that we were told, or something that it comes from a series of factual statements that we can follow to get our conclusion. Not looking for a pattern. If we're figuring out a pattern, that's inductive reasoning. But if it's coming from facts that we've been told or have read, or postulates or proven theorems, then we are using deductive reasoning. Example 1. First, we're going to take a quick pause to look at the difference between inductive and deductive reasoning. Here's our slight detour, and it's not in your notes. That's okay. We're going to decide if these are inductive or deductive reasoning. First hour begins at 7:15 every weekday. It is Tuesday at 7:15 a.m. Conclusion, first hour's beginning. So the question is, when we're looking at this, did we draw conclusions based on observations or based on what we were told? Since the first problem here, first hour begins, this is a fact right here, first hour. Since that's based on a fact, number 1 is deductive reasoning. The conclusion is based on deductive reasoning. Number 2, Samantha has allergies to mold and trees, but she loves to camp. She is planning to go camping in Michigan this fall, and Michigan is a high mold count state. Conclusion, Sam will have problems with her allergies. We didn't observe Sam, we were actually told about her allergies in the first sentence. So our conclusion is based on facts that were told to us. So this is deductive reasoning as well. Last year, Bill swam in a pool treated with bromine and had itchy red skin later that day. 2 months ago, after swimming at another pool treated with bromine, Bill had itchy red skin. Last week, Bill's parents bought a jacuzzi and treated it with bromine. After relaxing in the new jacuzzi, Bill had itchy red skin. Conclusion, Bill is allergic to bromine. Take a guess. These were all observations. Nobody said that Bill had an allergy to pool chemicals. So our conclusion that he's allergic to bromine was based strictly on observations, or we were told what had happened to him, but we weren't told about allergies. So this conclusion is based on what was observed, so it's inductive reasoning. Last one, Pat added 2 and 4 and found that the result was 6, an even number. Then Pat added 24 and 18 and found the result was 42, an even number. Lastly, Pat added 98 and 14, finding a result of 112, an even number. The conclusion is that Pat believes that adding 2 even numbers will always result in an even sum. So the question is this inductive or deductive reasoning? Well, based on the fact that it wasn't told to us about evens, this conclusion is drawn on Pat's observations. Therefore, this is inductive reasoning. All right, so now we're looking at deductive reasoning. An auto mechanic knows that if a car has a dead battery, the car will not start. A mechanic begins work on a car and finds the battery is dead. What conclusion can be made? Well, it follows the fact right there. The car will not start. Letter B, suppose the mechanic begins work on the car and finds that the car will not start. Okay. Can the mechanic conclude that the car has a dead battery? Well, not necessarily. This is what's known as converse error, where this is the statement right here, and the order follows, and we haven't really talked about that yet, but they know that if the battery's dead, with a dead battery, you don't have any power, you're not going to be able to start the car. So the dead battery leads to the car not starting. The car not starting does not lead to the dead battery. It could be that the battery's dead, but it might be something else. So no, it doesn't follow the same order, or doesn't follow the logical order. We'll talk about that order in just a second. If a number is divisible by 6, remember divisible means goes in evenly without a decimal, then the number is divisible by 3. 18 is divisible by 6. What can we conclude? 18 is divisible by 3. Based on that first sentence of what we were told. Now talking about the order is important because there are flawed arguments or illogical arguments if they don't follow a logical order. Sometimes our flaw actually lies in the fact that we don't have a true condition. Okay, maybe the car's battery isn't dead. Well, then it's not going to follow this sentence anyhow. But what we're talking about now is called the law of detachment. There's two laws that help us verify if something is valid logic. The law of detachment, I'm going to give you the symbolic notation first. If P, then Q. P happens. Conclusion, that's what those three dots mean. That means conclusion. Q happens. So what this is it's a law that says that we have to follow the conditional exactly as it's written. If these conditions are met, this will be the result. Okay? Assuming that that is true, if it's false, then the argument is invalid because of false premises. But if that's true, then whenever you have a case that first part, those conditions are met, the conclusion will follow. So if P, then Q. P occurs. Conclusion, Q happens. Let's take a look at this law in action. Given. From the given statements, write what you can conclude. If M is the midpoint of a segment, so we have to start with the midpoint, that's our P, then it divides that segment into two congruent segments, that's our Q. They're telling us next that M is the midpoint of AB. So that's matching our conditions. So then the conclusion is that AM is congruent to MB. If we wanted, we could draw a picture for that. M is the midpoint of AB. And that makes sense, and that's true, but talking about whether it's true or not is also valid because you have to have it to be true for it to be valid. But what we're looking primarily is it following the law of detachment? It is. If P, then Q. They told us that M is the midpoint, so that's a case of P. And our conclusion is Q, that two pieces are congruent. Letter B, if a baseball player is a pitcher, then the player should not pitch a complete game 2 days in a row. So if you have a pitcher, that's our P. Our Q is that they should not pitch the complete game 2 days in a row. Justin Verlander is a pitcher. That's P. On Monday, Verlander pitches a complete game. Conclusion, he should not pitch a complete game on Tuesday. It's following the order of the sentence. We're just following the order of the sentence. So in the next one, if A is acute, the measure of angle A is less than 90 degrees. they're telling us angle A is acute, the conclusion is its measure is less than 90 degrees. Not less than or equal, strictly less than 90 degrees. We're just following the order of the conditional sentence. It has to follow that order from P to Q. Using the law of detachment, does the law of detachment hold true for the following? If not, explain why. Well, I'm going to say this. If they tell you if P then Q, and then they give you Q and then P, that is called converse error. Why? Because instead of giving you the order P to Q, they gave you Q to P. And remember, writing Q to P is the converse. So this would be called converse error. So you could just say it doesn't follow the correct order, but if it's this reason, then it's converse error. So if it is snowing, there's P, snowing, then the temperature is less than or equal to 32 degrees Fahrenheit. So that's our Q. They then tell us the temperature is 20 degrees, which is not P, that's Q, and they're concluding that it's snowing. So they did P to Q, then they gave us Q, and now they're telling us P. This is what we call converse error. People think, hey, it sounds like they said the same thing, except they didn't. They said it in the reverse order, and the reverse order is not always true. It could be, but it doesn't have to be. So this is not following the law of detachment. It's what we say invalid. It's an invalid argument. It does not follow the law of attachment. You can just write invalid, doesn't follow the law of attachment, but I'm telling you the particular error is converse error. Try that for the next couple problems. Take a moment to read them, decide if they follow the law of detachment or not. Please pause the video to do this. Welcome back. If two segments are congruent, that's our hypothesis, then they are the same length. They're telling us here that they are the same, that they are congruent, so that is P, and their conclusion is that they are equal in measure. That's basically saying they're the same length. So this is a valid argument. It follows the law of detachment, which is P to Q, P happens, conclusion Q happens. If you are tardy 3 times, so there's our P, tardy 3 times, you must go to detention, so that's our Q. Andrew is in detention, that's Q. Conclusion, Andrew was tardy 3 times. Well, they used the same parts of the sentence, but they didn't follow the original if-then order. They did it in reverse. So this is invalid, and it's the converse error. Letter D, if the sides of a triangle are 5, 12, and 13, that's our P. Then the area of the triangle is 30 centimeters squared. That's our Q. Now they're telling us the area of the triangle and saying the side lengths are 5, 12, and 13. Well, just because that's the area, that they could be the side lengths, but they don't have to be the side lengths. So this, again, they didn't follow the order. It's invalid. It does not follow the law of detachment. They did P arrow Q, QP, which is converse error. We have one other law to determine if things are valid, and it actually has 2 conditional statements. It starts with 2 if-then statements, and then the last one is actually an if-then statement that is connected by the 2. Some people call this the chain, or sort of a chain rule, because they kind of follow like a chain or a sequence of events. The symbolic notation for this is if P, then Q. A separate if-then, if Q, then R. And then a conclusion, if P, then R. This is how proof writing works. When we do our proofs for 2-6, our geometric proofs, we're starting with some given information and we're making a statement about it, what comes after from a definition. And then we're taking that and saying, well, we can say something more about that. So we're kind of following a sequence of events. It's kind of like taking a trip somewhere. If I start at P, there's my starting point, and take it to Q, then I can jump on another mode of transportation at Q, to get me to R. So I can get, starting at P, I can end up at R, which that's the conclusion. If I start at P, I can end at R. So if P, then Q. If R, or if Q, then R. So if P, then R. Now, if it does not happen in this order, it might be okay. So here's the example of it being okay. If they tell me, well, you can get from Q to R and you can get from P to Q, well, then I just have to start at P to get to Q and then from Q go to R. So I can still conclude that I can get from P to R. I just have to change the order that those happen. However, if this connector, if you see this connector, you should see this part being the start. Here's our connector. Here's where we're going to end. Here's where we start. Here's our connector. Here's where we're going to end. And that needs to be the conclusion. If that's not the conclusion, then it's invalid. Here are some examples of the law of syllogism. If a number is prime, then it does not have repeated factors. Okay, prime is P, not repeated factors is Q. If a number does not have repeated factors, that's Q, then it is not a perfect square. That's R. So we're starting with the number being prime. The connector is not having repeated factors, and we're ending at perfect square. So our conclusion is, if a number is prime, then it is not a perfect square. Letter B, example 4B. If a quadrilateral is a square, then it contains 4 right angles. If a quadrilateral is a square, then it contains 4 right angles. If a quadrilateral contains 4 right angles, so there's our connector, then it is a rectangle. So the valid conclusion, here's our starting point, here's our connector, here's our end spot. If a quadrilateral is a square, then it contains, or then it is a rectangle. Which actually is true, and we will see why when we get to our unit on quadrilaterals. Apparently, example 5, which I wanted to give you, comes at the end of the notes. For some reason, I was wondering why they were missing on here. They were at the end. So we've already seen these. We discussed them. Feel free to see if you can try them on your own if you don't remember that from earlier. And feel free to rewind the video. Have a great day.